Hello everyone, I hope you're all doing well. In this video, we are going to solve this question. The question says metallic single crystalline material with FCC structure is stated. Hello everyone, I hope you're all doing well. In this video, we are going to solve this question. The question says a metallic single crystalline material with FCC structure is tested by a tensile test. Okay, a material is being tested by a tensile test, and the tensile stress is applied along the 112 direction. Tensile stress is actually the force, okay, that has been applied um, uh, along 112 direction. The direction of application of force has been given, that we can write as the direction of force. Okay, the force has been applied um, along 112 direction. Okay, this is one of the important information that we are given with. Okay, this is the direction of the force. 112 are the Miller indices of the force direction, and the critical resolved shear stress for the material is 0.34 megapascal. This is a constant quantity. Okay, and let us denote it with alpha with subscript C and R. C critical and R for resolved and shear stress afterwards. So 0.34 megapascal is the critical resolved shear stress. We are given with this information. It was found that this material can undergo plastic deformation due to slip on one bar one plane. So the material has the potential to undergo plastic deformation due to slip on that particular plane, which has the Miller indices 1 bar 1. So the slip plane is, we will call this plane as slip plane, because this plane can undergo plastic deformation due to slip, and let us call it as a slip plane, and its Miller indices are 1 bar and 1. In part A, we are told to explain the type of deformation that can be observed when the material is subjected to a normal shear stress, a normal stress below 0.75 megapascal. So we have to figure out that if this kind of material whose data is given above is subjected to a normal stress or below 0.75 megapascal, then what kind of deformation this material will show. Okay, so we have to find this out, and this is the part A. Okay, and the other parts will be discussed afterwards when we are done with part 8. Okay, in this video we are going to solve all of the parts, and yes, here I have written the data. The direction of force is 112. Okay, the force has been applied along this direction, and this is a critical resolved shear stress that we are given. This is 0.34 megapascal. Okay, and the slip plane is 1 bar 1, and the type of deformation we'll observe when the when the normal stress is below 0.75 megapascal. So we have to discuss which kind of deformation we'll obtain when the normal stress is less than 0.75 megapascal. This is the part A. Let's begin with the part A now. Now, in order to know which kind of deformation the material will show when it undergoes a normal stress, we have to find out the critical normal stress. Okay, the behavior in order to know the behavior of a material under normal stress, we have to find out its critical normal stress. Okay, so let us denote the critical normal stress by sigma y letter. Okay, and is now we'll write, we have to determine the critical normal stress. Okay, you can write in it words, critical normal stress denoted by sigma y, to know the behavior of material under subjected to normal stress. Okay, so we have to find out the critical normal stress, and the critical normal stress is given by the symbol for the critical resolve shear stress is this one. Okay, tau. It's tau CR. Okay, in subscript divided by M. M is the Schmidt factor. I don't know how to pronounce it, but it spells like that. Okay, this is m, which here m is equals to cos of phi into cos of theta. Okay, so we need to find out the critical normal stress, and the critical normal stress will be different for the different directions of the plane. Okay, and we'll discuss it now. Let us call this one equation as equation number 1. Now if we draw the plane 1 1 bar 1, then this plane is a triangular in shape. Okay, and I'm not going to waste your time by properly drawing it and finding out the lines making up the plane. Okay, I will mention it directly right there, because the student who requested me to do this problem has a very he has very less time left, so I can't, the plane 1 1 bar 1 is, it is triangular in shape. This is the plane. Okay, 1 1 bar and 1. All right, and you can see here that this plane is made up of 3 lines. Okay, or in other words, you can say that this plane is made up of 3 directions. It is made up of 3 directions. This is direction 0 1 1. If you find out the direction of direction corresponding to this vector, then it will come out to be 0 1 1. Okay, this is 1 1 0. All right, and this is 1 bar 0 1. All right, there are the 3 directions. Now you can see here the plane is made up of 3 directions. Okay, this is the plane, and these are the lines or the directions which make up the plane. Okay, so these are slip directions, you can also say it like that. They make 3 slip systems. All right, they are the 3 directions that the plane has. Okay, and each direction corresponds to a slip system. So we call so the slip systems are given by, or the slip systems are as follows. The slip system 1. So as I explained here, there will be 3 slip systems corresponding to a single plane, and they are 1 1 bar 1. Okay, for the you'll write slip system 1 1 1 bar 1, and the one of the direction will be taken into account. Let's say first is this one. Okay, we'll call this set as slip system 1. This is slip system 2. Okay, 1 1 0, and we'll have slip system 3 as 1 1 bar 1, and it is having direction 1 bar 0 1. You have to remember these directions for now if you have less time, but you can easily find out the Miller indices to these directions. Okay, so these are the 3 slip systems to a single plane. Okay, the plane can undergo deformation due to slip in these 3 directions. Okay, that is why we have divided them into 3 systems. We call them slip system 1 corresponding to this direction, slip system 2 corresponding to this direction, slip system 3 corresponding to this direction for the similar plane. Okay, the plane can undergo deformation due to slip in these 3 directions. Okay, if the force is applied along any of these directions, the slip will occur if the if the stress is large enough, and it will result into deformation. So what we will do, we'll find out the normal stress, critical normal stress corresponding to these 3 systems. Okay, and we'll find out what value we'll get. Okay, and after getting those 3 values for the critical normal stress corresponding to each of the system, we'll compare that value with the normal stress we were talking about. Okay, we'll compare it, and after that we'll come to know that which kind of deformation we'll obtain after applying this normal stress. Okay, the comparison needs to be done, and for that purpose we need to calculate the sigma y, which is the critical normal stress, and sigma cr is already known. We need to find out m, where m is cos phi into cos theta. Now let us find out cos phi and cos theta for each of the slip system. Cos phi is constant for a system, but cos theta will be different for different slip systems. Okay, cos theta will be different for 3 of them. Let us first find cos phi. Now cos phi is obtained by here cos phi is obtained by taking dot product between the applied force which was in 112 direction and the normal for normal to the plane, means the vector which is normal to the plane. Okay, and we know that if the plane has similar indices 1 bar 1 1 bar 1, then the vector which is normal to this plane will be a vector with the similar Miller indices. Okay, so normal to plane is actually 1 1 bar 1 again. Okay, so we know that in general we'll have a dot b is equals to ab cos of phi. Okay, and if you want to find out cos of phi, ab will be divided into this side, and where a and b are the magnitudes of these vectors, or if we can say in other words directions. Okay, so what we have to do is cos of phi will take the dot product between these two vectors, and I write them in coordinates from 1 1 2 dot 1 minus 1 1. Okay, dot product between these vectors divided by the magnitude of each of the direction. So magnitude is obtained by taking the square of first coordinate plus taking the square of second coordinate plus taking the square of third coordinate, which is 2. 2 square is 4, that is why, multiply by magnitude of the second vector, which is this 1 square. Square to the minus 1 is again plus 1, and square to 1. Okay, and dot product occurs by multiplying the corresponding values, first to first, second to second, third to third. Okay, so 1 into 1 is 1, plus 1 into minus 1 is minus 1, and plus 2 into 1 is 2. Okay, I hope you know how to find out the dot product. I'm not explaining it too much in order to shorten the video length. It's 1 plus 1 plus 4, which makes up 6 under root 6 into under root 3. Okay, and 1 minus 1 gives 0, plus 2, which is 2 divided by under root 6 into under root 3, and if you calculate it using a calculator, then you will get 0.471. yes, cos of phi comes out to be 0.471. Okay, now we know cos phi. Let us call this as equation number 2. Okay, what was equation number 1? Yes, this was equation number 1. We know the value of cos phi now, and what we now need to know is cos of theta for slip system 1 plus for slip system 2 and for slip system 3 separately. So for slip system 1, we'll call its cos theta 1. Okay, corresponding to it. Now theta cos theta 1 is obtained by taking dot product between the slip direction and the direction of force. For cos phi, we had to take the dot product between the vector normal to the plane and the applied force, but for theta, for cos theta 1, we have to take the dot product between the slip direction and the force in force direction, which is 1 1 2. So for slip system 1, this is the direction, so we'll take dot product between cos theta 1 equals 1 1 2 dot 0 1 1. Okay, this is the direction we are going to consider, and I'll write it in coordinates. Sorry, 1 1 2 dot 0 1 1 divided by under root of 1 square plus 1 square, their magnitudes. Okay, so 1 into 0 is 0, plus 1 into 1 is 1. Corresponding values will be multiplied to each other. 2 into 1 is 2. Under root of 2 square is 4. 4 plus 1 plus 1, which gives 6. And this is under root 2. Okay. And 2 plus 1 is 3, divided by under root 6, multiplied by under root 2. And it gives, if you use calculator, okay, the value you will get for it for 011 is 0.8666. Okay, you can confirm it using a calculator. This is the value of cos theta 1, okay, for the slip system 1. Now we are going to find out the value of cos theta 2 for slip system 2. Okay, we will mention for slip system 2, cos theta 2 is equals to, I will write it in terms of coordinates, okay, and direction of force is 112, and we'll take the dot product with 110, which is the slip direction number 2, and we'll divide it with the magnitude of these vectors. You can easily elongate that question as much as you want, because you know there are the several steps that we are there are several unnecessary steps that are you know, not as much needed right now at that level of study. So taking square of 1 plus square of 1 plus square of 2, square of 1 plus square of 1, square of 0 is again 0, so I'm not mentioning it here. Multiplying 1 with 1 plus 1 with 1 plus 2 to 0, okay, it's under root 6 here, multiplied by under root 2, and it's 2 over under root 2 into under root 6, so that the value of cos theta 2 for the direction 110 comes out to be 0.5777. okay, you can confirm it by calculating 2 by under root 2 into under root 6. okay, now we are going to find out the value of cos theta 3 for slip system 3. okay, they are the three directions that the plane has, and hence it forms three slip systems in which the deformation is possible due to slip. And cos theta 2 cos theta 3 now cos theta 3 will be equals to the product of 1 1 2 dot with the third direction, which is 1 bar 0 1, okay, separated by commas because I'm writing them in terms of coordinates. okay, you can represent a vector by corresponding coordinates. okay, and under root 1 square plus 1 square plus 2 square multiplied by under root minus 1 square means 1 again, so I'm not mentioning it here. 1 into minus 1, it's minus 1. okay, 1 into minus 1 is minus 1, 1 into 0 is 0, 2 into 1 is 2, and under root it's 6 again, multiplied by under root 2, and it's minus 1 plus 1, minus 1 plus 2 gives plus 1 in, and here it is, and if you calculate it you will get 0.288. okay, this is cos theta 3. okay, so we have found cos theta 1 to be 0.8666, cos theta 2 0.577, okay, and cos theta 3 as 0.288. okay, designation of the names to the slip directions and slip systems is arbitrary. For example, if I took this as slip system 1, then that selection was arbitrary. You could have selected this one as the slip direction 1, slip system 1 and 2 and so on. This is not specific, it's arbitrary. You can choose as you wish. So now we are going to find out. So Schmidt's okay, I don't know Schmidt, okay, Schmidt Schmidt factor for three slip systems are m1 equals cos theta 1 cos phi, okay, and m2 would be equals to cos theta 2 cos phi. Cos phi is common in all of them, so m theta is equals to cos theta 3 cos of phi. So we'll put simply the values here and we'll get the value of m1, m2 and m3. cos theta 1 is 0.86. It will multiply it with 0.471 that we got for cos phi, and the result is so multiplying it will give us 0.407886. okay, and for cos theta 2 we'll do it multiply by 0.471. okay, and we get, make sure to do the same all of these calculation by yourself too, so that you may not face any difficulty at the final time, because sometimes we do not do our calculation by our hand and it results into the lack of confidence. So yeah, these are the m1, m2 and m3 values, and we already know the value of critical resolved shear stress. Now we just need to put the values into the equation number 1, so that to get the critical normal stress values for all the slip directions. So we'll do it for the direction number 1. okay, direction number 2. These values will help us to determine which kind of deformation is possible when the normal stress of certain value which is given is applied, okay, which is I think 0.75 megapascal. So let us put the value 0.34 megapascal, okay, divided by m1 0.407886. okay, let us divide both of these values, and 0.833 4 oh sorry 6, which we can round off as this megapascal, is one of the critical value, and it's 1.25 megapascal. okay, and similarly for this one it's 2.5 megapascal. okay, so these are the three critical values, and the least critical value is 0.834, while the second one is 1.25 megapascal, and the third one is 2.5 megapascal. Least to maximum value is 2.5, while the least value is 0.834. This minimum stress is needed in order to produce plastic deformation. okay, if the normal stress which is applied to the material is less than this least critical value, then deformation will not be plastic but elastic. okay, since applied normal stress which is 0.75 megapascal is less than the minimum critical normal stress which is 0.834. It's larger, so larger force is required to produce the plastic deformation, and if the stress is less than this value, then the deformation that is produced in a material will be elastic. okay, so yeah, critical normal stress of this, then the material hence the material will undergo elastic deformation. So in this way the question has been done. okay, we have successfully discussed which type of deformation was possible for the material under this force, okay, under this stress. So stress is force per unit area in terms of pressure. So yes. Now let us do the part B. okay, let me read the statement. And so in part B we are told to determine the yield strength of this material, and after that in part C we are required to determine the active slip systems. okay, Determine the active slip systems on the given slip plane 1 bar 1, which is given to us. We have to find out the active slip systems. Active slip system means which slip systems will operate, which means where the deformation will occur. That causes plastic deformation when the applied stress reached 2 megapascal. If the applied stress reaches 2 megapascal, then which slip systems will be active, and hence in which directions the material will be deformed. Okay, so we have to determine that. And yes, let us do these two first. To determine the yield strength of the material, and yield strength of the material is the minimum stress needed to produce or initiate plastic deformation in a material. Okay, so we know that the minimum stress that is needed to produce plastic deformation is 0.834 megapascal, as I told earlier. 0.834 megapascal is actually the yield strength of the material. At this point, the material will start to be deformed plastically. So it is 0.834 megapascal. All right, the part B is done. Now we are moving to the part C, where we are needed to determine the active slip systems. It's S here. Okay, so the applied stress is 2 megapascal. All right, since the applied stress is 2 megapascal, which is 2 megapascal is greater than 1.25 megapascal, which is sigma y2, and which is greater than 0.834 megapascal, which is sigma y1. Okay, but it is less than 2.5 megapascal, so this slip system will not be active. Okay, when the stress of 2 megapascal is applied, then this slip system will not be active, because greater force is required to produce plastic deformation along this system. Okay, so the plastic deformation will only occur into slip system 1 and slip system 2, which requires lesser force to produce plastic deformation. And we can see here the applied stress 2 megapascal is greater than the critical stress, normal stress of these two systems. Hence, slip system 1 and slip system 1, which is you have to mention it 1 bar 1. Okay, with corresponding direction 110. I think it's 110. Let me see it. It's 011. Okay, 011. And slip system 2 1 bar 1. Okay, 110 direction. Are active slip systems under stress 2 megapascal. Okay, part C is done. Now we are going to do the part D. Part D says if the Young's modulus of this material is 0.6 gigapascal and Poisson's ratio is 0.3, calculate the largest reversible strain in the diameter direction if the sample is cylindrical. Okay, the Young's modulus is given. We'll call it as E, capital E, as to be 0.6 gigapascal, and Poisson's ratio is given. We have to find out the largest reversible strain. Okay, let us do it. Capital E, which is Young's modulus, 0.6 gigapascal. Okay, giga means 10 to the power 9 pascal. Okay, and Poisson's ratio is given 0.3. We need to calculate the largest reversible strain. We'll call it as E with D and D in subscript. Okay, we need to calculate it. We know that largest reversible strain is given by Poisson's ratio, negative of Poisson's ratio multiplied by E with subscript LL. Okay. Here Poisson's ratio is known, but ELL needs to be determined. Here ELL is further equals to the critical stress, minimum critical stress, okay, which was sigma y1 divided by the Young's modulus. Okay. Now we'll simply put the values. Minus 0.3 multiplied by sigma y1, which is the minimum normal stress, critical normal stress, which was 0.834 megapascal, and capital E, which is 0.6 gigapascal, which could be written as into 10 to the power 3 megapascal. Okay, you can put the value of mega as 10 to the power 6, and here giga as 10 to the power 9. It's the similar thing. Okay, doing the calculation. So it results 4.17 multiplied 10 to the power minus 4, and if we remove 10 to the power minus 4, then taking the points backward, 1 2 3 4. Okay, so this is the largest reversible strain in the material, and you can round off it as 7 makes 1 as 2. Okay, you can round it off. So this is the final answer. All right, and it is done now.